So we are continuing our discussion on LTI processing of Weissan stationary random processes with an example. Okay, so what is this example about? In the earlier hour, previous hour, when x of t is Weissan stationary, we have seen that if I apply a filter on this random process, which is Weissan stationary, I get another output process, and this is also Weissan stationary. This is what we have shown. Now, let's have an example on this. X of t, h of t, y of t, same processing chain. X of t is zero mean Weissan stationary process. H of t is, this is a filter with impulse response given like that. Now, the question is, find the moment descriptions of y of t. This is this, this is this. So this is the application of our result. So let's also erase this. So number one, so I should calculate this mean function. So this is expected value of y of t. Okay. So how can I calculate this? Maybe we can use it from our memory. This is expected value of x of t times, h of s when s is evaluated at 0, what we call this DC gain. And this is just a constant. Why it's constant? Because it's Weissan stationary. And that constant is actually 0. Okay. So since it's too black, it's Weissan stationary. And I have, this is equal to 0, as you see. Since this is 0 mean, and the final result is equal to 0. That is good. Now, the second one, output autocorrelation. So let me write this one last time, like this. Expected value of t minus tau. Also, let's put the conjugate, even though everything is real valued over here. So I have what I call Ry of tau, okay, from our earlier discussion. So this is a function of tau only. Function of tau. No problems. We have derived this in the earlier hour. And furthermore, I know that Ry of tau is equal to Rx of tau, input process autocorrelation, convolution with h of tau, impulse response with the variable tau, convolution with h conjugate minus tau. Okay. So my only issue is then calculation of this. So if I can calculate that, that would be giving me this Ry of tau function also. And we are done. So let me do this. Okay. So why am I singling out this part? Because h of t is given to me, and let's see what kind of calculation is this. So this is convolution of h of tau, this function, with flipped and conjugated version. But conjugation does not do anything over here because everything is real valued. I can even neglect this conjugation. Okay, that's fine to neglect it for real values, real valued signals. So how should I do this? So I would like to define, actually, again, sorry, Rh of tau, something like this. Let's keep the conjugation for generality. So this is more like a definition. And this is called deterministic. You will remember from earlier courses perhaps, autocorrelation. Sometimes you don't say deterministic because in other signal processing courses everything is deterministic. So this is the autocorrelation function of h of t. Okay? But for our purposes, there is nothing random over here. So I need to calculate this function from here. So what's the meaning of this? Well, let me do a sketch. So h of tau. What is h of tau? H of tau is this function with the variable tau. Okay. So in between 0 and t of the argument, it is equal to 1. Okay. And for the other values, these are all open, it's equal to 0. Open is equal to 0. Now, one more sketch. So how about h of minus tau? H of minus tau is, okay, let's put the conjugation over here. So this is 1, this is 0. This is the function that I call the flipped version. If you assume that there is a mirror over here, okay, whatever you see is flipped on the side of the mirror. Okay, I mean, that is the reason we call this like, you know, flipping operation and so on. The reasoning is very simple. So these sketches, you may consider this h flip if you wish. I mean, it's very basic signal processing, but maybe first course of signal processing you are studying such things, but we should be clear on this. So h flip of tau for positive values, for positive taus, is equal to h of negative taus. And they're all equal to 0. H of taus, this sketch is valid. So for the flipped version, so you see these negative quantities over here are mapped to the positive quantities over here. This is the reason it's like flipped version of this. Okay, so what should I do? I should take the convolution of this one and this one. So I should take the convolution of this one with this one. Okay. So how do you do the convolution? There is also a flipping in the convolution, am I right? Okay. Maybe I should write this first as convolution. So if I write this as a convolution, h of, let me a dummy variable. Do you agree? Convolution of the first argument, second argument, something like that. So this is infinity to infinity, dummy variable. Let me put the conjugate over here for the second one. So I need to flip this. So one thing is, in an ordinary signal processing course, all variables are t, maybe n, k, etc. Over here, we have different variables, tau, t1s, t2s, convolutions. You have to think about these convolutions carefully. The way you think about these convolutions is looking at the dummy variable that will be integrated out, tau prime over here, and the output variable will be tau. Okay? So do you agree that this is equal to this? Do I have a mistake over here? First function, okay. Second function, call this second function of tau. So this second function of variable minus dummy variable, okay. But there is minus because it's defined like that. We are done. So actually, what we see is the following. Now, if I take the convolution of this, so this function, with respect to, if you wish, tau prime, is present over here. Now I shift this function by tau units to the left, to the right, etc. Let me shift it like this. So this is like t over here, tau. tau plus t. So this becomes h of shifted version of this. Very basic signal processing, as you see. Now I have to multiply this function, and this function. So this binary value, either 0 or 1. So this is either 0 or 1. Am I right? So the result is either 0 or 1, and then I should find the area under 0, 1 function of it. So this is the product. Let me put the conjugation if you wish. Conjugation. Then I should do this product. But in this drawing, tau is positive. Am I right? Tau is clearly. This tau variable is positive, but it's less than t. I mean, clearly. Maybe I don't need to even write this, because this says that this tau is in between 0 and t, but just for clarity, I have that. Now what's going on? So you may think about this template function. This template function is this. This function is multiplied by its shifted versions. This is what we call the autocorrelation function. Do you remember from signal processing courses? There is convolution and autocorrelation properties, etc. In 301 especially. Maybe you have seen this. So what is the result of this operation? So if I do the convolution or autocorrelation calculation like that, what do I get? Can I sketch it over here? So this is RH of tau. So one more time, this is h of tau. It is this. So when tau is equal to 0, what is the result? Tau is equal to 0 is, actually, this case. You move this to this leftmost corner and do the multiplication of number 1, first term in the integrand, and number 2, you do the multiplication of these functions and find the area under them. So what is the result over here? T. 1 is also okay. I agree, because I totally agree with you, because it seems that everything is normalized to 1, but it's t. Because you have this function multiplied by itself. There is no shifting going on. Okay, that is it. So if I have a tau, let's say over here, like tau is somewhere over here, let's say. T is over here. That means that I have to calculate the area of this part. Am I right? So what is the area of this part? If you multiply this one and this one, so you calculate the area. So if I shift it towards right, the area gets smaller and smaller and smaller, and that is it. So what is this area? T minus tau times 1, area of this rectangle. So actually, I think it will be clear. So it will be a straight line starting from t. Why is a straight line? Well, we see that if I move towards right, this side of this rectangle gets smaller. This is constant, 1. So I see this. So how about for the other part? Or let me do this. For if tau is greater than t, then this function is multiplied by its shifted version, but shifted version has no overlap with the original function. Okay? Shifted version is maybe shifted to 5t. So number 1 is over here, number 2 is at 5t. If you multiply them, you get always 0. So you get this. So how about for negative parts? Now this original function, this time, you're moving this template function towards left and looking for what we call the inner product between those two functions. You multiply those two functions and calculate the inner product. So again, if you shift it more than t units to the left, same story happens. I think it will be again something like this. Okay? So if you check this, this is, what's the equation? T minus tau. This is t plus tau. Tau is equal to 0, tau is equal to this, and so on. Okay? So maybe if I need to write this, t minus absolute tau for tau, let me write more clearly, piecewise defined, minus t and t, and this is tau, 0 other. Okay. We get this. So what we have seen, maybe you will remember, this is the deterministic autocorrelation in action. Maybe this is not news to you, but in case you have forgotten, this is the way you calculate, deterministic autocorrelation. So what we see, now I have one more convolution actually. This is the deterministic autocorrelation convolved with another one, and that will be the final result for the output autocorrelation. Okay. That is it. So final result is, so Ry of tau is Rx of tau, convolution with, writing it one more time, h of tau, h of minus tau, and this is what we call Rh of tau, and this is this. Okay. Okay. Now let's make some comments on this. Let's erase this part. Comments. Number one, let's assume that x of t in the earlier problem is a Gaussian process with autocorrelation. Rx of tau, delta tau. Okay? So I'm talking about this Rx of tau. And furthermore, something new, Gaussian process. So this part is new. Then, output process is also, we know the following, Gaussian. And Gaussian, let's say, with mean function, mean mu y of t is equal to 0, and Ry of tau is equal to Rx of tau, convolution with h of tau, h of minus tau. But this is given as delta of tau, impulse. So this becomes then, this is what we call deterministic autocorrelation. Deterministic autocorrelation itself. Okay? Because this is the convolution with impulse. If I sketch this, i.e., the output autocorrelation is Ry of tau is this. So this is what we have as Ry of tau function. And let's just make a note, Ry of t is equal to 0. Now, let me see. So let's find the joint density of, let me see, y4 plus t over 2, y4 plus 3t over 4. Okay. So how can I find this joint density of these three output variables at the fourth second plus t over 2 and so on, three variables. So again, I will be writing this ya, yb, yc, yb, yc. This is Cy matrix this time. And I have e to the minus, the Gaussian, this time one more time with minus 1/2 y minus mu y. Cy to the minus 1 y minus mu y. Actually, this distribution, the form of the distribution is, even the form of the distribution is important to us. This is the reason that I'm writing it again and again. And it's also, you can see that it's a little bit important. Why it's important? I can calculate this output mean function. I mean, there is some operations going on, but these are operations that I can do even on paper. These are easy operations, that kind of operations, convolution operations, that type of operations. At the end, if I calculate the mean function and the autocorrelation function, I can get the density, as you see. So this is the density at the output. It's a big deal. Now, in this example, what is mu y? Mu y is all zero vector, because it's zero mean, we have said. So we sometimes show these zero vectors like 0 and underbar. All elements are equal to 0. Now how about Cy? This is the covariance matrix. So this is a, as you can imagine, pairwise covariances of three elements. So which one is Ya? So just for the sake of easy writing, I will call this Ya. I will call this Yb, Yc, okay? Because I cannot write that strange number, over here or as an index like that. So over here, what do I have? This element is, again, Ya. Pairwise, I have said, covariances. You multiply these two, okay? Actually, I should maybe write it like this in general, but this is zero mean. Means are equal to 0, so I'm not even writing them, okay? So you multiply these two variables, take their expectation, okay? So expected value of Ya square, Ya, okay? So this is autocorrelation evaluate at zero length, output autocorrelation. So this is, let me write with another color, T. Okay, because this is expected value of y4 times y4 Ry 0. Time difference is equal to 0. So how about this? These two. What is the time difference between these two? Time difference of the arguments, t over 2. So I should calculate Ry t over 2. For t over 2, I get this. Midpoint. So R, A, and C. A and C. So time difference is 3t over 4. Midpoint of this and that, I guess. Or let me write it, sorry. Let me write it like this, t over 4. Okay. I think we get the idea, isn't it? So from this autocorrelation information, I can write this density very easily if I can fill in the entries of this matrix. But entries of the matrix is nothing but evaluation of this function at some points. Okay. So for example, this one, B and A, again difference is t over 2. So difference is 0. So this one is B and C, difference is t over 2. Am I right? Difference is t over 2. So I get this. Actually, this matrix has a structure, but that's good enough for our purposes. So is this the end? This is the end of this calculation, because now you have this matrix. You can calculate its determinant if you wish. That will be a number over here. Take the square root of that number, another number over there, and so on. So again, now previously this covariance matrix in the earlier example, it was a diagonal matrix. And we had made a comment that if this matrix is diagonal, then the random variables are independent because they are Gaussian distributed. Please remember that. Right now it's not diagonal. So if I this time focus on this part of this matrix, so what kind of operation is this? Now this is Y transpose Cx inverse, because again this is zero mean in our case, Y. Okay. So Y transpose is Ya, Yb, Yc, and we have this 3 by 3 matrix over here. Erasing this part. Ya, Yb, Yc. Okay. Do we agree? So I should take the inverse of this matrix. This is my Cy matrix. This is the Cy matrix. Let me put inverse to emphasize this inverse. Okay. So after I calculate the inverse of this matrix, I do this kind of a calculation. And what do I get at the end of this? If I do this calculation, I get a, so this is 1 by 3 vector. This is 3 by 3 matrix. This is 3 by 1. So at the end, I get a scalar, am I right? It's a 1 by 1. So 1 by 1. I get a scalar over here. Okay. So what's my comment? Given a Ya, Yb, Yc values, for example, 1, 2, 3, you evaluate this and you get a number over here. It should be like that. This is the value of the density at that point. Okay? That is it. So you may think that this is something complicated, but it's nothing but multiplication of this A, B, C quantities with some weights. But the issue is this is called quadratic product. This is called quadratic product. The reason is, at the end, you multiply, a bunch of numbers are present over here. At the end, you have Ya times Ya at some point. Okay? Ya times Yb. Okay? So it's like a quadratic in 3 variables. A, B, C are those variables. So it's a quadratic in 3 dimensions. This is the reason that this is called quadratic product. Okay, so we got more insights into this Gaussian distribution, as you see, and we have seen that why this autocorrelation function, covariance function is important, because these are giving us the distribution immediately of the output process samples by just evaluating these functions at appropriate locations. That is it. Now, what else can I say? Comments, more comments. Comment number 1. Comment number 2. So the Gaussian process with our x of tau, delta tau, autocorrelation function, as in comment 1, comment number 1, is called, I will explain this further, white noise. Okay, I will explain this further maybe in 10 minutes or so. Note that So let's say this is Rx of tau, and mu xs as a function of t is equal to 0. Okay. So we see that any two distinct samples of white noise process I will erase this part because it doesn't have to be Gaussian, it's more general. The process with this autocorrelation being impulsive function, as in command 1, is called white noise. Okay. This. We see that any two distinct samples of white noise process are uncorrelated. Okay. So that means that Rx of tau is equal to 0, mu x is equal to 0, when tau, both of them, when tau is not equal to 0. Okay. That is the meaning of this. It's everywhere equal to 0, autocorrelation function, except when they're identical. So this is a rather, maybe a singular definition because of this impulse. Okay. But this is the definition of white noise. Okay. Again, I will say more things on white noise immediately after this discussion. The output process of the earlier example has autocorrelation Ry of tau like this, minus t and t. Okay. That means that any samples of y of t process with any two samples of y of t process with separation greater than t seconds are also uncorrelated. Actually, I mean, this is not a news because this is Ry of tau is equal to 0 and mu y is equal to 0 for tau greater than t from this function, clearly. So that means that, this information means that y of t and y of t minus tau, okay? So this is my first sample, T1. This is my second sample at T2, okay? Are uncorrelated. Okay, this is the definition that we have, okay? So this function being 0 means they're uncorrelated. But furthermore, specific to this example, since yt is Gaussian, uncorrelatedness, let me write it like this, is equivalent to, let me write it maybe like this, 3, independence. But don't be confused. For Gaussian processes, uncorrelatedness is equivalent to independence, okay? So again, emphasizing the important point one more time. So what else? Let me see, 41, 42. So does this make sense? Well, let's think about, so how did we get this? We have got this by processing input x of t by an impulse response h of t. This was y of t. So let's say at the input side I have a, x of t like that. Okay. So what was impulse response? Impulse response was flat in the first t seconds. Okay. So that means that output is, if you do the convolution kind of reasoning, so for the output at this second, y of t, you are calculating the area of this function in the last t seconds. Okay, that becomes the output, convolution operation. Flip this, shift it, do the convolution. Okay, so at the t second, you are this is like area calculation. Convolution is nothing but the area calculation. So you flip this template, shift it, multiply by this x of t, and do this area calculation. So this tells us that at the time tx, okay, if I check the output, I see nothing but a linear combination of what I have at time tx at the input, black curve, and earlier values up to t seconds earlier. Okay, so this value is just summation of them somehow. So if you check another time, let's say another time, let's say it's ahead of this, something like this. If you check another time ty, so this is another area calculation. This is ty. So this is this area calculation. But this is composed of, again, so this area will be the output at time ty. So this is y ty. So clearly see that this says that whatever you get as a number over here and a number over there at the end of this area calculations, this says that they are independent because they are Gaussian distributed and they are uncorrelated. The reason is, you may think about it like that. Now the input of this filter, they do not overlap. And these input samples, as we have said, the input samples of this filter, they are independent from each other. So if there is no overlap of these, there are no common samples. Okay? So if you don't have any common samples, then of course the input of this filter is independent from the input of this filter, then the outputs are also independent. Okay? So the only way that I have a correlation or dependence between them is they should be somewhat common. So this is the reason that this separation by t comes up. Okay? So this is this comment. That means any two samples separation by t are also uncorrelated. So these are mathematical results as you see, but they have important consequences, interpretations like that. Maybe this is the first time that you are seeing it, but if you think about these results, you will be finding them more and more natural. So that is it. Now I would like to make the white noise definition, and no more calculations, just the definition, and that will be the end of this hour. White noise definition, and that will be it. But let me, okay, white noise. So we have seen that by processing Weissen's stationary random processes, RP, random processes, with LTI systems, we can shape in quotations the autocorrelation structure of the output for the shaping of output autocorrelation or synthesis of a desired random process with a given autocorrelation for a given desired autocorrelation LTI processing can be helpful and practical. The white noise is a definition, and it's more like a mathematical definition. In practice, you cannot have a white noise value process. It's more like a mathematical definition, like something like an impulse response. Okay? When you are first learning the impulse response, so you always ask, how can I find the impulse? Is there a impulse function generated and so on? Of course, you can approximate an impulsive behavior, very short pulse and so on, but in practice, we don't have impulses also. Impulse is more like a mathematical definition. So similarly, we have a process called white noise. If number one, mu s of t is equal to 0. Number two, Rx t1 comma t2. And 2 different times is f of t1 delta t1 minus t2 Rx t1 t2 is equal to 0 when t1 is equal to t2. That's the case. Let me write this. Node 2 or condition 2 says that two samples of white noise are uncorrelated. However, they are close to each other. It's a very strange thing if you think about this. For example, in the stock market and so on, maybe you can see curves like this, and there are people are fitting trends and saying, okay, this is a normal trend, this is a bottom edge, so it's like things like that. Okay. So the issue is now this function, for example, from the prediction point, you know the value of this function at this point. Maybe this is today's stock market price. So we are interested in tomorrow's, or a second later stock market price. So this says that if this is not a white noise, this random process, it says that whatever you are close, this is the 5th second. So I have the 5 plus epsilon second. Epsilon is a very small non-zero number. It's uncorrelated. So uncorrelated is seconds to the independence ratio, isn't it? Uncorrelated and independence, they are similar but different. But for Gaussian processes, they are the same. So this is the reason that it's more like a mathematical definition, because we don't expect a signal to change that suddenly. So this epsilon is arbitrarily small, meaning that epsilon can be 10 to minus 10, maybe 10 to minus 100. Do you see what I mean? However, it is small, but when t1 is not equal to t2, so just a microsecond, nanosecond away from that time, you get something, if it's Gaussian also, independent. So do you think that it's like wildly changing signal? So this is the reason, as I have said, it's not something practical, but we are using this understanding to generate other random processes with reasonable autocorrelation, something like this. Okay, now I want to discuss the special case. This is called stationary white noise. Actually, this is wide sense stationary because it's all about. Now, mu x of t equal to, so this is equal to 0. Rx t1 t2 is equal to this delta t1 minus t2. So why do I call this wide sense stationary white noise? We had a small battery problem. We have replaced the battery of the microphone and we are continuing. We are rewinding actually this part and then rewriting it one more time. So for the stationary white noise, as I have said, this is Weissen's stationary because there is nothing about densities as you see. This is all about moments. So it is zero mean, constant mean, and if the autocorrelation function is a special case of this, meaning that this part is not changing by time. So this is constant, it's not changing by time. So then this becomes a function of, as you see, t1 minus t2. But this is not a function of t1 minus t2. Even though this is function of t1 minus t2, this is changing by t1, as you see. Okay? So this is not Weissen's stationary, but this is Weissen's stationary. And this is called Weissen's stationary white noise. Okay? Or sometimes, you know, in general, we mean this when we talk about white noise. Okay, that's all for today. So we will be continuing from this point on Wednesday.